Train a neural network on billions of images, and it identifies a face. But against a standard business database, it loses to 20-year-old decision trees. Convolutional neural networks dominate vision because their architecture assumes a spatial prior. Pixels share a single unit of measurement, and their location matters. Translate a pixel grid of a cat 2 steps left, and you still have a cat. But tabular datasets lack spatial symmetry. Swap the tenure and charges columns, and the predictive meaning doesn't change at all. Unlike pixels, the columns in a database are completely heterogeneous. They do not share units, scales, or logical boundaries. Tenure is a count of months, while charges are currency. Categorical columns, like a contract type or a merchant ID, pose an even harder geometric problem. They are discrete labels, not quantifiable numbers. Month to month is not mathematically larger than 2 year. Gradient descent requires differentiable functions acting on continuous inputs. To feed a category label into a neural network, you have to force it into a numerical matrix. Every method of forcing that conversion introduces structural noise. Deep learning struggles on tabular data because the actual geometry of a spreadsheet rejects the spatial and continuous assumptions that neural architectures require to function. Industrial tables are full of step-shaped truth. A credit rule activating at a score of 620 creates a sharp perpendicular boundary in the data. A smooth, continuous neural network wastes massive computational capacity trying to approximate this staircase shape with a slope. It rounds the corner and smears the boundary across a wide neighborhood. A decision tree natively maps this exact structure. It expresses the sudden jump in risk using a single, hard split along the axis, learned from whatever data sits right on that boundary. We can observe this architectural advantage directly by measuring default baseline performance on standard datasets. This bar chart shows a performance comparison across an all-categorical dataset and an all-numeric dataset. The tree ensembles reach higher accuracy margins across both datasets compared to the neural network baseline, without requiring per-dataset tuning. Gradient-boosted trees win the tabular domain. They succeed because their architectural bias exactly matches the inductive reality of business data. The modern landscape of gradient boosting is defined by 3 distinct engineering bets. XGBoost bet on systems engineering. LightGBM bet on speed. CatBoost placed its bet strictly on statistics, engineering a solution to 2 severe algorithmic leaks. The first leak occurs when handling categorical data. Because decision trees require numbers to compute a split, data scientists routinely rely on target encoding to force text labels into a numerical format. Target encoding replaces a categorical label with the historical mean of its target outcome. We can observe the mathematical leak with a 2-row dataset for a single category. Row A has a positive outcome, a 1. Row B has a negative outcome, a 0. If we calculate the standard target mean, both rows receive a feature value of 0.5, but half of that encoding is derived from the row itself. Row A's new feature value actively contains its own answer. The standard repair for this is a leave one out protocol, where a row is encoded using every row except itself. On a small category, this breaks entirely. Row A is encoded by row B's label, resulting in a 0. Row B is encoded by row A, resulting in a 1. The repair is perfectly anti-correlated with the truth. Standard target encoding is a statistical trap. It forces the model to cheat by explicitly leaking the future outcome into the past training data. A common professional misconception is that a standard k-fold cross-validation loop will catch and isolate this target leakage. If the encoder is fitted globally before the split, the designated validation folds have already contributed their target labels to that global mean. The test is poisoned before the model even trains. CatBoost isolates this leak using its core statistical innovation, ordered target statistics. CatBoost shuffles the dataset and imposes an artificial time axis over the rows. Under this artificial time, a row can only be encoded using the target labels of the rows that preceded it in the sequence. Row 5 is encoded using the information from rows 1 through 4. Rows 6 and beyond remain inaccessible. By enforcing a strict historical sequence, ordered target statistics algorithmically seals the leak. It makes it impossible for a row to consult its own future. There is a second, deeper statistical flaw that infects every standard gradient-boosted decision tree, regardless of whether the data is categorical or numeric. This is a subtle, compounding bias in how standard algorithms calculate their gradients, known as prediction shift. Standard boosting works sequentially. Tree 2 is built specifically to fit the errors, or residuals, calculated by Tree 1. The flaw lives inside this loop. Tree 1 was trained on the exact same rows now being used to calculate those residuals. The gradients are inherently biased by self-inclusion. While this mathematical bias is tiny in a single round, it compounds exponentially across hundreds of boosting iterations. CatBoost solves this compounding error through ordered boosting. Ordered boosting computes a given row's residual using a temporary model trained exclusively on rows that do not include that target row. CatBoost operates on one uncompromising mechanical axiom. A model must never be allowed to consult a row's own label while learning how to treat that row. Algorithmic purity only matters if it survives the realities of production. Real-world tables arrive dirty and unpredictable, breaking models before training even begins. In tabular machine learning, dirty data often carries genuine business meaning. A blank billing total on a spreadsheet usually indicates a brand new customer account, not a random system error. This code snippet shows a schema contract. It is the single programmatic defense against silent failures and data drift. You must strictly raise errors for corrupted numeric columns. If a future data delivery puts a stray text string in an expected tenure column, this pipeline stops loudly, preventing a silent failure. Conversely, the contract intentionally coerces blank billing totals into native nans. This allows the model to naturally handle structural missingness without inventing fake data points through careless imputation. A schema contract is not a disposable preprocessing script. It is a rigid, executable guarantee, applied identically to your training data today and your serving data tomorrow. The final failure point of tabular modeling is evaluating performance with vanity metrics that hide the truth. Standard accuracy is mathematically useless on imbalanced business data. If a company has a 26% customer churn rate, a model that constantly predicts nobody churns scores 74% accuracy while providing zero business value. You must prescribe the correct metric pairing. Use ROC-AUC to measure the pure ranking quality of the model, combined with log loss to penalize falsely confident probability estimates. Finally, all evaluation is subject to the ultimate operational rule, the vault. The law of the vault is absolute. A stratified test set must be locked away before any schema or modeling work begins. It is touched exactly once by the final model to produce the only performance number that matters. Succeeding with tabular machine learning requires respecting the table's geometry, sealing algorithmic leaks at the gradient level, and guarding your evaluation with unyielding discipline.